The Torrance Refinery is a 750-acre facility located just outside of Los Angeles, California. At the time of the explosion, the refinery was owned by ExxonMobil. An important part of the refining process takes place in the facility's fluid catalytic cracker, or FCC unit. In the FCC unit, heavy hydrocarbons from crude oil are broken or cracked into smaller hydrocarbons, which can then be processed into gasoline and other fuel products. The heavy hydrocarbons are first fed into a reactor, where they mix with the catalyst. The heavy liquid hydrocarbons are converted into lighter hydrocarbon vapors as they travel up the reactor. At the top of the reactor, the lighter hydrocarbon vapors are separated from the catalyst. The hydrocarbon vapors then flow to the main distillation column. The catalyst falls down the side of the reactor, where it moves through a slide valve to a piece of equipment called the regenerator. During the reaction, a layer of carbon called coke forms on the catalyst that must be removed. Inside the regenerator, air is added, and the coke on the catalyst is burned off. The catalyst is then fed back to the reactor through a slide valve, and the cycle is repeated. When the coke is burned off the catalyst, this creates products of combustion called flue gas. The flue gas flows out the regenerator and enters a system comprised of multiple pieces of equipment, which remove any remaining catalyst particles present. The regenerator and flue gas system comprise the air side of the FCC unit. The last piece of equipment in the flue gas system is called the electrostatic precipitator, or ESP. The ESP removes small catalyst particles using static electricity. While the ESP is energized, it creates sparks, which are sources of ignition. It is critical that the flammable hydrocarbons in the reactor do not flow into the air side of the FCC unit, as this could create an explosive atmosphere. To avoid this hazard, the two slide valves connecting the reactor and regenerator are used to maintain a catalyst barrier between the pieces of equipment. The sequence of events that eventually led to the explosion at the refinery began on Monday, February 16, 2015, when a piece of equipment in the air side of the FCC unit, called the expander, vibrated forcefully enough that the refinery's control system automatically transitioned the FCC unit to a standby mode known as Safe Park. During Safe Park mode, the flow of hydrocarbons into the reactor is turned off. The flow of air into the regenerator is also stopped. The two slide valves connecting the reactor and regenerator are closed to ensure a catalyst barrier is maintained. Steam is then forced into the reactor to prevent hydrocarbons in the main distillation column from flowing back inside. The ESP remains energized during Safe Park. One slide valve, however, had eroded over 6 years of operation, and even though it closed, it could not maintain a catalyst barrier in the reactor. Within 7 minutes of the unit going into Safe Park, all of the catalyst in the reactor fell through the slide valve into the regenerator. A direct pathway was created for hydrocarbons to flow between the reactor and the regenerator. But the pressure of the steam flowing into the reactor as part of Safe Park mode was high enough to prevent hydrocarbons in the main column from flowing back inside. With the unit in Safe Park mode, operators attempted to restart the expander several times, but were unable to do so. Refinery personnel met to identify a strategy to repair the expander and bring the FCC unit back online. Operations personnel predicted the expander could not restart because catalyst had likely accumulated inside. On Tuesday, February 17th, a meeting took place involving a group of refinery personnel. The group discussed a similar expander outage that occurred in 2012, for which the refinery had developed what is called a variance. A variance is a management-approved deviation from procedure. The group decided to use the 2012 variance, which allowed a departure from the typical requirements for isolating the expander. Part of that process involved installing a blind in one of the expander's outlet flanges. On the morning of Wednesday, February 18th, ExxonMobil maintenance attempted to install that blind, but were unable to do so because steam was escaping through the open flange. Steam from the reactor had traveled through the leaking slide valve into the air side of the FCC unit. Using the variance as a guide, the flow of steam into the reactor was decreased in an attempt to reduce the amount escaping from the expander. But the variance did not evaluate whether this flow rate was sufficient to prevent hydrocarbons from flowing into the reactor from the main distillation column. And unknown to the operators, light hydrocarbons from a separate unit had flowed through a leaking heat exchanger into the main column, increasing pressure inside. With the flow of steam reduced and less pressure in the reactor, nothing could prevent the hydrocarbons from flowing back from the main distillation column. The hydrocarbons flowed into the reactor, where they escaped through the leaking slide valve into the air side of the FCC unit. At 8:07 a.m., a maintenance supervisor working in the FCC unit received an alarm on his personal hydrogen sulfide monitor, warning him that hydrocarbons were leaking nearby. By 8:40 a.m., multiple workers around the expander received the same alarm, and the FCC was evacuated. In an attempt to mitigate the problem, a supervisor ordered the flow of steam to the reactor to be increased, but it was too late. A flammable hydrocarbon mixture was flowing through the air side of the FCC unit and moving toward the ESP with its multiple ignition sources. There, the flammable hydrocarbon mixture violently exploded.